Okay, so in this video, we're going to do a few things. First of all, we're going to define what we mean by an acid or base in two different ways. And then we're going to look at how we define what we call the strength of an acid or base and how we can tell by looking at the formula for an acid or base whether it is weak or strong. And then finally, we're going to look at what happens when an acid reacts with a base in what we call an acid-base reaction. So, one way of defining acids and bases is according to what's called the Arrhenius definition of acids and bases. And in this definition, we define an acid as a substance that, when it's dissolved in water, produces hydrogen ions. So we have our acid, it's in aqueous solution, but it actually exists as aqueous hydrogen ions and an anion. Now, sometimes our acid actually can produce more than one hydrogen ion, and we'd know that because there would be a subscript here in the formula. In the Arrhenius definition of acids and bases, we say that a base is a substance that, when it's dissolved in water, produces the hydroxide ion. And so in this definition, all of these compounds called bases will be metal hydroxides. They're all going to be ionic compounds. And normally hydroxides are insoluble in water. There's a couple of exceptions, and there some of the elements from group 2+ form soluble hydroxides, and the group 1A metals also form soluble hydroxides. Now, a hydrogen ion is simply a proton because a hydrogen atom is just one proton and one electron. And it turns out that protons, when they're dissolved in water, interact very strongly with water molecules. In fact, so strongly that they form a covalent bond to the water molecules and create what's known as the hydronium ion. In fact, it turns out that we never actually see isolated hydrogen ions in aqueous solution. They are always present as hydronium ions. So, keeping this in mind, when we think about an acid getting dissolved in water, what's actually going to happen is a proton will be transferred from our acidic molecule to a water molecule. So here we go, that's going to happen. So this guy is going to lose an H+, and that leaves behind the anion Cl- in this case, and the water molecule is going to gain an H+, producing the hydronium ion. So this kind of really clearly explains what's happening when this acidic molecule is dissolved in water. So we see what's happening is a proton is being transferred to the water. Now, while we know that hydrogen ions are always present as hydronium ions in aqueous solution, you frequently will see people making the little shortcut of, instead of writing out H3O+, they're going to write H+. One way of thinking about what happens between an acidic molecule and water is that the acid acts as a proton donor to the water, which is acting as a proton acceptor. And this leads to what's known as the Bronsted-Lowry definition of acids and bases, which states that an acid is simply a proton donor and a base is simply a proton acceptor. So under the Bronsted-Lowry definition of a base as being a proton acceptor, this gives rise to the possibility that we can have molecular species that are bases. And these are often nitrogen-containing compounds. So when I take one of these nitrogen-containing compounds that functions as a base, what will happen is it'll act as a proton acceptor when it's dissolved in water, and the water will actually this time act as a proton donor or acid. And so what is formed is a cation and the hydroxide ion. Now, many of these molecular bases are important in biochemistry, and a good example of that are the 4 DNA bases. You'll find, if you look at their structural formulas, that they are all nitrogen-containing compounds, And they're called bases because when they're dissolved in water, they accept a proton from the water molecules, and this gives rise to the formation of hydroxide ions. So one characteristic of both acids and bases is what we call their strength. And the strength reflects the extent that the acid or base forms ions in aqueous solution. And it's a pretty simple definition. It's kind of an all or nothing. Strong acids and bases completely, 100% of the molecules will form ions when they are dissolved into aqueous solution. Whereas weak acids and bases incompletely form ions when they are dissolved in aqueous solution. So it's important not to confuse the strength of an acid or base with its concentration, or also to confuse it with its reactivity. Some acids and bases are very reactive, perhaps they're highly corrosive, but they're still characterized as being weak because they don't meet this requirement of completely dissociating into ions when they are dissolved in water. So we can look at the formulas and recognize whether an acid is strong or weak. There are two sort of groups of acids that are strong. And so there is this group of acids here called they're called hydrohalic acids, or they're called binary acids sometimes. We've got hydrogen chloride, hydrochloric acid, hydrobromic acid, and hydroiodic acid. So this is a hydrogen atom combined with a group 7 element. These guys are all strong. And like I said, they're often referred to as binary acids. And then we see this other group of acids here that are always strong. And these are acids that contain oxygen. You see that? Oxygen there. And how we know it's strong is if the number of oxygens, I'm going to draw with the mouse here, is greater than or equal to the number of hydrogens in the formula of the acid plus 2. So if you look here, we see we have 1 hydrogen and 3 oxygens. So that guy is strong because 1 plus 2 equals 3. Here we have 2 hydrogens and we have 4 oxygens. So this guy is strong because 2 plus 2 equals 4. And here we have 1 hydrogen and 4 oxygens, and this guy is definitely strong because 1 plus 2 is 3 and 4 is bigger than 3. So when we look at weak acids, what are the weak acids? Well, hydrofluoric acid is weak, and it's kind of in a category by itself. You just have to memorize that that guy's a weak acid. Hydrofluoric acid is a little weird. It's classified as a weak acid because it doesn't completely dissociate into ions in aqueous solution, but it's really chemically reactive. It's incredibly corrosive, this stuff. It can eat bones away. Phosphoric acid is an example of one of these oxygen-containing acids where you don't have enough oxygens, right? You only have 1 more oxygen than hydrogen atoms here. So that means that it's classified as weak because you need at least 2 more oxygens in order to classify it as strong. So any acid where you don't have enough oxygens to be strong is going to be classified as weak. The third class of weak acids are these acids that have this group of atoms on the end here, this COOH, and they're referred to as carboxylic acids. I'm trying to write with the mouse here, which is a little awkward, but I'll write that out. So carboxylic acids, and they're the ones that have that COOH grouping of atoms on the end, and they're all weak. Any acid that has this grouping of atoms is classified as weak. So they're your big categories of strong and weak acids. So you guys need to be able to look at the formula of an acid and then decide, is it strong, which means is it a binary acid where it's hydrochloric acid, hydrobromic acid, hydroiodic acid, or is it one of these oxygen-containing acids where we have enough oxygens to make it strong? To recognize that it's weak, there's one special class of hydrofluoric acid. It just happens to be weak. And then we have the carboxylic acids where we have this COOH group of atoms. And then finally we have these oxygen-containing atoms where we don't have enough oxygen, right? So a key thing for you is to be able to look at the formula of an acid and decide if it is weak or strong. Now, classifying bases as being weak or strong is a little bit easier. All of the strong bases are metal hydroxides, and they're normally either group 1A metal hydroxides or they're group 2A metal hydroxides. You've got to be aware that the group 2A metal hydroxides actually contain 2 hydroxide ions per formula unit. So all strong bases have OH minus as part of their formula, and they're all ionic compounds. Your weak bases, the ones that don't completely dissociate into ions in aqueous solution, are going to be your nitrogen-containing compounds, and perhaps the most famous of these is ammonia. So keep an eye out for ammonia. That's going to be your stereotypical weak base. Frequently, I will tell you that a substance is a weak base, but you definitely should be able to recognize that metal hydroxides are strong bases and that ammonia is a weak base. So finally, we get to talk about how acids and bases react with one another. So what happens when an acid reacts with a base is that the hydrogen ions formed by the acid will react with the hydroxide ions formed by your base to make water. So H plus plus OH minus will give you water. So we can write the total molecular equation, the total ionic or overall ionic equation, and also the net ionic equation for an acid-base reaction, just like we were doing for precipitation reactions. So here I've written the total molecular equation for the reaction between sodium hydroxide and hydrochloric acid. And you want to take note of this because this is what you did in the lab when we were titrating that mixture of sodium hydroxide and sodium carbonate. So here we have hydrochloric acid reacting with sodium hydroxide, and the product of this reaction is soluble sodium chloride and water. And so people will often characterize the reaction between an acid and base as being summarized like follows. You have an acid plus a base makes a salt and water. And by salt, they just mean some kind of ionic compound. But in the reaction between hydrochloric acid and sodium hydroxide, it literally is salt, table salt, sodium chloride. So a salt just is another way of saying an ionic compound. Okay. So here we have the molecular equation for this particular acid-base reaction. And none of our compounds have been dissociated. Now we know a few things. This is an ionic compound that's soluble, so it really exists as individual ions in aqueous solution. This is also an ionic compound that is soluble, and so it too will exist as individual ions in aqueous solution. This here is a covalent compound, and it's going to exist as intact molecules in aqueous solution. This compound over here is a strong acid. So that means that it's not going to exist as HCl molecules in aqueous solution, but rather it's going to exist as hydrogen ions and chloride ions. So if we dissociate any strong acids or any soluble ionic compounds into their individual ions, we get the total or overall ionic equation. And that's what I've done here. So this strong acid exists as ions, so I've written it as the individual ions. This ionic compound here exists as individual ions because it's soluble. This ionic compound, because it's soluble, exists as individual ions in aqueous solution, and this is a covalent molecule, so we're going to leave it intact. So what we've got here is the overall ionic equation, where all of those things that exist as individual ions have been written simply as the ion. And when we look a little closer at this, we see that some of the ions, the sodium ions and the chloride ions, exist in exactly the same form on both the products and reactant side of the arrow. So what we can do is we can go ahead and cancel those guys out, and then that gives us what we call the net ionic equation. Now the ions that we cancel out are referred to as spectator ions. They're the ones that just kind of are sitting there doing nothing. So once we cancel out the spectator ions from the overall ionic equation, we get the net ionic equation for this reaction. So one proton, which comes from our hydrochloric acid, reacts with one hydroxide ion, which comes from our sodium hydroxide, to give us 1 mole of water. Okay, so that definitely concludes our section on acid-base reactions. So what are acids? Well, acids are proton donors, according to the Bronsted-Lowry definition, and bases are proton acceptors. Acids and bases react with one another in what is referred to as a neutralization reaction. The products from this reaction are an ionic compound, or what's sometimes called a salt, and water. We can write an acid-base reaction in 3 different ways. We can write a molecular equation, an overall ionic equation, where we dissociate any strong acids or strong bases. We dissociate any soluble ionic compounds, but we leave everything else intact. And when we cancel out the spectator ions from our overall ionic equation, we're left with what's referred to as the net ionic equation.